Good morning, everybody. Welcome to this second day of the MAAGC edition 2024. So it's a great pleasure to introduce Minyoung Jeon from University of Georgia. And we're going to hear about method classes of sugar varieties via smaller solutions.
Thank you for organizers for inviting this workshop. And I'm gonna talk about this mother class. So here the mother class. This mother class is Jeon mother class is first defined by Pearson in 1974, and this mother class was introduced to have the topological Euler characteristic of singular varieties. So at that time, the topological Euler characteristic for the smooth variety was already defined using Torre-Jeon class. So Pearson defined for the similar characteristic invariance of this and for the singular varieties. And here our object in this talk is the Schubert variety, especially the Schubert varieties in the Grassmannian. The Grassmannian of D type, B, C, and D. So if you know the Lie algebra, we have this Schubert variety, and especially we are looking at this the types B, C, and D. And today's goal is to compute this mother class of this Schubert variety. Schubert varieties, especially using these small resolutions. So I will define each terms later in this talk. So at this point, you just assume that we are going to compute this mother class of this Schubert variety. And for the basic background, so I'm gonna review some concepts, the basic concepts. So here, so a variety is the level of solutions of polynomial equations. So for the affine spaces, you can think about this circle. X squared y equals 1. This is the solutions of this circle equation is this. So actually this circle is variety. And we also need to know this projective space of dimension m. And the projective space is given by this n+1 vector space over complex numbers, and you just exclude this origin, and then you function by this equivalence class, where this equivalence class means if you take the some vectors in the complex space, then the equivalence means this vector is given by another constant times this y vector, where the lambda is inside of these complex numbers, and we should not include this 0 So the projective variety X inside of this projective space, it means this variety is defined by the set of solutions where the polynomial equations is the homogeneous polynomials. So that means each term of these polynomials has the same degree. Defined, given by the solution set. Of homogeneous polynomials. So the basic example of this projective variety be this non-singular very surface given by
Ladies and gentlemen, now your attention please. Flight CA8360
It's announcement from the leaders. Yeah. So we are some here we are in this example. So we the example of this projective variety is the non-singular quadratic surface with its homogeneous equation. So the degree of two equations in three-dimensional projective space, and this projective space is actually coordinated by this variable, four variables x, y, w, z. So it is a four-dimensional vector space, and you just mod out this zero part. So this the solution set of this equation is actually inside of this. That then we can have this equation, this variety for this. So and we also need to know the concept of this Grassmannian. So the Grassmannian is denoted by ZR K, some vector space V. So let's say the dimension of vector space is n, the usual vector space, and this Grassmannian is just parameterizing some vector space, the sub-vector space of V, where this dimension of U is just a K. So you just collect K-dimensional subspaces of the ambient this vector space V. And here, if we just think about the Grassmannian of two planes in four-dimensional space, then we can think of this element of this Grassmannian as the spaces generated by these two column spaces. So you just think about each column generate these two-dimensional subspaces of the dimension four-dimensional space. Or the another element of this Grassmannian would be 1 A B 0 0 C 0 1, something like that. So you just choose any basis among these four bases. Let's say this one is E1, E2, E3, E4. So you can choose two bases from out of these four dimensional spaces. So you can write down this element of this Grassmannian in terms of these matrices. And as you can see, the dimension of this Grassmannian is the number of these free variables. So the dimension of Grassmannian tree in this case is 2 times 2. And in general, the dimension of the Grassmannian tree, where the dimension, if this dimension of V is n, then the dimension of this Grassmannian is k times n minus k. So you just think about this k, the bottom k rank, the k rank, and the left is just the free variables, k times n minus k. And then the Grassmannian, we can have this group action. So if we just think about the special linear group of this matrix, n by n matrix, with the determinant of A equals 1, then we can, this group, SLV, actually can act on this Grassmannians. So that the stabilizer of this element, or the specialized stabilizer of this Grassmannian is given by some parabolic subgroup. So you just think about the block matrix, the block of triangular matrix with the size of this first block size of A, and the second block is n minus k, A, and n minus k. So this the parabolic subgroup action of this Grassmannian stabilize this Grassmannian, so that the Grassmannian of k subspaces inside of V can be identified this SLV over this parabolic subgroup. So here, and let's define the Schubert variety in type A Grassmannian. So the type A Grassmannian means our the group action would be this GLV. And the Schubert variety varieties in this Grassmannians is are defined by defined as follows. So here we just take this we just fix this vector space V of dimension, the n-dimensional vector space generated by E1, E2 up to En. And then we just fix a complete bag V1, V2 up to Vn, where this dimension of Vi is just I. So you just list a vector space one by one from the linear the third dimensional spaces like this. And then we take this partition alpha, the weakly increasing sequence or partition, alpha k. And the last component of the sequence or the partition must be less than n minus k. So here the k is from this Grassmannian, and the n is from this dimension of this vector space. And then given this setup, we can define this Schubert variety. I'm gonna use this S for the Schubert variety. Is defined by the set of vector spaces, sub-vector spaces, satisfying this dimension condition. So the dimension of this intersection with is alpha I plus I, having at least I dimensions for all I. So we can define this Schubert variety using these dimension conditions on the intersection of some spaces inside of this Grassmannian with some fixed flat, some partial fixed flat. And then some properties of this Schubert variety is the Schubert cell is when this dimension conditions as the exactly same as this dimension I or I. Then this Schubert cell is isomorphic to some affine spaces of the dimension of this sum of these partitions. So for example, if we take the alpha equals 2, 3, and the Grassmannian of 2 and 3, where this dimension of 3 equals 5, then the Schubert cell can be somehow expressed by this matrix like this, so that you just think about the alpha 1 plus 1 is 3 as the dimension L is 1, and alpha 3 the intersection with this column space with the whole spaces. Then for alpha equals 2 plus 2, so 5, the dimension 5. So overall this dimension is just L is to like 2. And then the second property of this Schubert variety is if we set up this partition as strictly not strictly weakly decreasing partition, then the setup is contained in the Young tableau of shape k times n minus k. So the Young tableau means you just take some these blocks with k row and n minus k columns, or vice versa. Then this partition is that sit inside this Young tableau. Then the Schubert variety as the cellular cohomology class as some sure polynomials, say it's 1 up to the xk. So the class, the cohomology class, this is a cohomology class. The cellular cohomology class in the cohomology of Grassmannians and this homology of this Grassmannian is has the basis or is generated by this Schubert classes. So there are a lot of the Schubert varieties inside of this Grassmannians, and each class, each cohomology class generated this cohomology of these Grassmannians. And each homology class of this Schubert variety is given by this Schur polynomials. And then the Schur polynomial means if you have this partition mu, then this Schur polynomial is given by some determinant of mu I plus j minus I in some matrix of size of the length of this partition. So if you have this length 3 partitions, like alpha 1, alpha 2, alpha 3, then this is a 3 by 3 matrix. And this the Schur polynomial is given by this determinant of some homogeneous symmetry polynomials. So here this h k x1 of x n is just a sum of these powers. Yeah, so k means the sum of these powers are just a k, and you just collect these terms of degree k. Here, I'm gonna use different notations. So this is L, K, L, K. And the another property of this Schubert variety is the classes of this Schubert polynomial and Schubert varieties is self-dual. So the Schubert variety, the class of this Schubert variety has a dual in other Schubert varieties given by some another partition, where this partition lambda is just a complement of this k by n minus k Young tableau of this partition U. Questions? And here today's goal is to study the type D Schubert variety. So the type D Schubert variety means you just take the vector space of 2n dimensional 2n dimension. So dV is 2n dimensional vector space. So you just think about the space generated by 2n elements. Then this vector space V has some symmetry by linear form. So the bilinear form is given by V1, V2, and it's a V1 transpose with some anti-diagonal of the identity matrix of size n. And we make two different spaces. And as in type A cases, we can define these orthogonal Grassmannians. So the maximal orthogonal Grassmannians. Grassmannians. Like the n-dimensional isotropic subspaces in 2n-dimensional vector space. Then this orthogonal Grassmannian has actually divided into two connected components. One is OG prime, and the other is OG double prime, depending on the parity conditions. So if you take some isotropic subspaces of V, or this is isotropic subspace of V, the maximal isotropic subspace of V of dimension n. Then depending on this the parity conditions on this dimension of this intersection, these orthogonal Grassmannians are divided into two disjointed connected components. And inside of each orthogonal Grassmannians, we can define a Hilbert variety. Either one of these orthogonal Grassmannians. So here, similarly, to define these Hilbert varieties, we just take this partition alpha. This time you have this strictly increasing partition of the length s. And once you choose this strictly increasing partitions, then you can take this partial flag. Given by this partition, alpha s, where this dimension of V alpha I is alpha I as before, as in type A. Then this Hilbert variety, the Hilbert cells in this orthogonal Grassmannians is given by the dimension on this intersection of L and alpha V alpha I equals I or Y. So we can define this Hilbert cell in type D. I think orthogonal Grassmannians, either of them, using this dimension condition. Yeah. And then the Hilbert variety is the closure of this Hilbert cells. So because of this parity conditions, we cannot directly define this Hilbert variety with this inequality. So instead, we just define this Hilbert cell first, and then take this closure to have this the Hilbert variety in the orthogonal class. And then using this Hilbert variety in type B, we wanna study some other class of Hilbert varieties. So let me define this mother class. Yeah, this definition is really hard. So yeah. So here, that X is a projective variety. Of the dimension N. It's fit inside of this projective space of a more bigger dimension. And then we just think about the Grassmannian bundle. So the Grassmannian bundle of N on the tangent space of this projective bundle over this projective space. So the fiber of this bundle is just a tangent space. at this point on this X. This is the Grassmannian bundle. Over projective space, and inside of this projective space, we have this projective variety of dimension n, and then we can construct some rational map P by sending the point on this X to the tangent space of X. And then the Nash block V is from this X theta to X, where this X theta is the closure of this graph. So the G is the graph of this phi. So here X is inside of this variety, the smallest part of this variety, X, the projective variety. And the image of this X is the tangent space. So the G is just a graph of that, the graph of this phi. Then this X theta, X G bar, the X theta is the closure of this graph. So the Nash block is the closure of this graph to the variety X. Then this V is isomorphism over this smooth variety, smooth part of this variety. And then the Nash tangent bundle T. So for the smooth variety, we just take the tangent bundle, but because the variety is singular, so we take this Nash tangent bundle, and this Nash tangent bundle is defined by some resolution map on this X theta. And using this Nash tangent bundle instead of just the usual tangent bundle, we can define the model class. Of M as just a push forward of this Nash tangent bundle of the homology class of this Nash tangent bundle on this Nash law. Questions?
So when you define the Nash tangent bundle, this calligraphic T is S restricted. What is S?
The S is a homology bundle. On this Grassmannian, so you just think of this n-dimensional vector space at some point. So we just restrict to that bounded by this Nash law. And then the small resolution is actually the resolution. So the resolution means you can actually, if you have this singular variety, then you can get rid of some singular points using some kind of this map. So and then over some certain some open length subset, there is isomorphism. So if you think about some variety without the singular points, then this smooth part is isomorphic over this resolution. And we say this resolution is smooth if we think about these fibers. So just think about the inverse image of the point on this X. Then this dimension of this fiber. So you just collect some fibers where the dimension of this fiber is at least 5. Then the small resolution means the set of these fibers satisfying these dimension conditions has co-dimension 2i greater than 2i. So if you just collect some fibers that has a dimension, let's say 1, then the co-dimension of this fiber, the set of set of these fibers has 2. Yeah, the co-dimension is written. So the small resolution has this kind of properties. And B. Jones in 2010, he showed it like this. So if we have characteristic cycles, so this is just a sum of on some variety using some linear combination of monomer bundle. So I'm not gonna explain what it is. So you just think about there's some invariance properties on this variety for the characteristic cycle. This is the characteristic cycle. And if this characteristic cycle is irreducible, so when you expand this characteristic cycle, then you have just only one compound, one part. Then and if we have this small resolution, then the model class of X, so the CM means the model class of this variety X, is given by just push forward of this small resolution on this Chang class of this tangent on this level. Because the resolution is smooth, so we can avoid defining this Nash tangent bundle. So we can use this resolution to have this model class of this variety. So in this way, we can avoid some hard definition of this Nash law and Nash tangent bundle. We can more simply define this model class using this small resolution. And by Bo and Fu in 1997, they show that the Schubert variety varieties in the Grassmannians of types A, E, and E. So the A is just special linear group, and B means the group is special orthogonality of rank 2n. So by Bo and Fu says that the Schubert varieties in type A, D, and C, D and E has this irreducible A6 side. So Jones in 2010 he used this relevance case. It's a small resolution to compute this model class of high Bayesian virtual varieties. And for type D, I calculate this model class using this Sankara Nathan small resolution. So yeah, let me give you the construction of this Sankara Nathan small resolution. So here Sankara Nathan small resolution. So here the Sankara small resolution means we just take the true virtual variety in type D. And there's some assumptions. For the resolution to make this. So I'm not gonna explain the assumptions, but the assumption is somehow giving some conditions on this partition. Then under this assumption, we can concretely construct some small resolution of this virtual variety by some product, some resolutions inside of some product. Where this each component satisfies some incidence relation. So here each component, let's say uj, is inside of this cross matrix of a j plus 1 inside of some spaces given by, so these spaces wrj and wlj, these are just one over u beta, and this w and v alpha, where this v alpha is just a complete isotropic flag.
How do these resolutions compare to like Bott-Samuelson resolutions, which are more common, I think, right?
Actually, these are the same type of Bott-Samuelson resolution. So, the Bott-Samuelson resolution is you take this tributary variety with this product of variety, I mean Rachmaninoff over some quotient. So this is the same type, but we just write down this each component as just some. It is the same Poissons, but we use this vector space as particle. Yeah, great. Any other questions?
So who is beta? You say one of U beta, B alpha.
Oh, U beta is one of these components. Beta is one or E or something like that. And this V alpha is when you define this Hilbert variety, we have this complete flag.
Yes.
Yeah, so these are from this complete flag. So the incidence relation means you, let's say you have this kind of relation. And these two left and right are decided by the equivalence relations from the Bose-Samuelson. Yeah. Uh, yeah. So, yeah, these are just a small resolution. So what this Anchor and Vinci-Nathan did, they take some Bose-Samuelson resolution, then characterized the fibers, dimension of these fibers, and show that the conditions of this. And then I use this Hilbert or the small resolution of this type, the Hilbert varieties. And then using the residue formula. Here the bar residue formula means you have this variety, the smooth variety with this torus, means the torus section means you have some diagonal matrix. So you add this diagonal matrix on this variety, like the Hilbert variety. So the variety, Hilbert variety is given by some subspaces. So we can actually add by some torus action using this matrix form. Then say this P is just some polynomial associated some vector bundle. Then the integral of this polynomial with some classes like Hilbert class is given by some of the torus fixed point of this variety. This is the equivariant part. T over the sum Chang class of equivariant Chang class of the normal vector space of this F. Yeah, this is very technical, so yeah, I'm not gonna explain this one, but I use this theorem to calculate this mother class. So the pushboard of the tangent bundle on this small resolution. So if we use this tangent bundle, then this the Chang class of tangent bundle is given by some polynomials in the vector spaces like this. So I use this Chang class, the CTG, the Chang class of tangent bundle on this resolution, and then I intersect with this small resolution to push forward that the Torah Chang class of small resolution to the just the original variety, the Hilbert variety. So this is quite technical, so I'm not gonna explain everything. So yeah. So the main point is I use this small resolution and this was residue formula to calculate this mother class in terms of Hilbert classes. So here so if we apply this small resolution and our residue formula, then we can write down this the mother class of this small resolution and mother class of this Hilbert variety as the sum of the some coefficient of the sub Hilbert classes. So just think about some some classes, the homology classes of the CW homology of this orthogonal class magnets. For type A, this is just a short polynomial. So can expand this model class in terms of the classes of this Schubert variety. And this coefficient of this expansion in Schubert classes is given by this first the tangent bundle of this small resolution intersects of this small resolution of this Schubert variety. And then if you calculate this coefficient, then you will see that all this coefficient is just a natural numbers.
Should some of the alphas be betas there?
Here the beta is the strong variety. This is the multiplication of this Euro Schubert variety. Because we wanna find out this coefficient, so the Schubert class with the Euro Schubert classes, then they just trivial. So I multiply by the Euro Schubert variety to find this coefficient of the model class. And these numbers are just a natural number. And if you list, so let's say this is if you take this example as 3, 5, and then if you list all these sub partitions, like 1, 4, 2, 5, 3, something like that. So you just find all these sub partitions contained in these 3, 5. Then these coefficients alpha beta satisfy some additive unimodality condition. So the coefficient is just increasing and then decreasing in positive. Questions? Yeah, I'm gonna use this method for the type C and B. And because the characteristic cycles are not irreducible because it is not type ADE. So in this case, if we apply the same method to obtain this Kazdan the classes. So it's another class, another characteristic classes, but instead of this model class, we obtain this assumption. So yeah, I'm gonna stop here and thank you for listening.
Thank you for your lecture. Any questions or comments? Feel free to-
For the type B and C, are you still considering the same type of small resolutions?
Yes. Same type of small resolution, and the conditions for the distance is a little bit different. But still the construction.
I'm assuming there are other types of small resolutions. Can your method be extended to other types of small resolution? What is sort of unique to this particular type?
I think the type E has a similar resolution like this, but the other types like the exceptional types have or G, then yeah, we don't know. But of the classical types, this is C. I mean, you can also another small resolution, but this is one of them.
Sorry, now you threw this teaser out in the last line and I have to ask, so the Kaushal unlisted classes. I mean, yeah, were they invented to do some of the Kaushal, the classical Kaushal unlisted theory, or do you know their relationship to that representation theory, geometry, combinatorics? I mean, they're called that, right? Or were they just discovered by Kaushal and Lustig for some separate purpose, maybe? I mean, it could be.
Yeah, I
Uh-huh.
actually don't know this.
Yeah, the history, that's fine, I was just curious.
Yeah,
Yeah, no worries, I can look it up, it's fine. I mean, it's fine, I just thought if you knew, yeah, thanks. Thanks for considering.
So maybe like a follow-up question. So you are saying the segment is only in type B and C level. So what happens like in say type A? Is there like a characteristic type A version?
Cosmology classes doesn't require this small part, small resolution. So every type, if you have this push forward with this resolution, then you have this cosmology class. So they define very recently about this classes. So yeah, I actually don't know the history of this part, but yeah, any resolution, if you have any resolution, and if you take this push forward of that resolution, then you have this cosmology class.
Do they also mention type A?
Yes, yeah, they mention the arbitrary correct.
There also a definition of bigger resolution. I guess you could make the code dimension to be smaller than something, maybe.
I know the semi-small resolution. I haven't. Yeah, or the big resolution. Yeah.
So the final answer you get for these coefficients R, alpha, beta is a formula as like a determinant or Foppian, something like that.
The alpha beta is just a number. But when you calculate this, this part, then this is the Foppian. This part is Foppian.
So my question in the spirit of like Suihang's chat yesterday, is there any chance of a combinatorial interpretation for these as counting something?
I don't think so, yeah. But this pattern and the model class is actually can give you some Euler characteristic of this variety. So here for the Euler characteristic of this sphere, you just count surface point spaces, and if we and this sphere is smooth. But if we take the some singular variable, then if we use this model class, then you can actually calculate this Euler characteristic of that variety. So if we connect somehow to the combinatorics, maybe from there, but yeah, it's that I don't know. But the coefficient has some combinatorics, like we studied.
You said in the model is a log. Okay.
Yes, yeah. Crazy.
But you mentioned the short variety inside the Grassmannian. It Are you also thinking about similar setting for inside the like variety?
As for the flag varieties, I don't know the small letter. But with my Graham and Scott at UGA, we just somehow construct some small resolution over more general variety called the chaotic flow. So right now we're still working on it. We just on the irreducibility of this characteristic size. So I think that resolution might be the one for the flag variety case. Because if we just specialize the K or we can specialize K or distribute. So that might be the one, but at this time, at this moment, we don't know.
And could you say something about how the mother classes relate to whether you can say something about the charge person person?
The uncharged MAAGC classes are just or I'm gonna say this way. So the model class is the linear combination of these charge-charged MAAGC classes with the coefficient as the local Euler structure. So if we know this model classes and the Euler expression, we can recover this charge MAAGC. So they are related to each other. Actually, the model class is model class. Then they define.
So I was wondering if you can use the small resolution to compute the CSM classes. Yeah, what the order abstraction is of the.
Yeah, we need all abstractions. So yeah. It's yeah.
Questions? Or also, if you are connecting over Zoom, please unmute yourself and ask a question. Not the case. And we have 1 hour of break, so we resume here at 11, and let's think about it again.